What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, only to be reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore ignite like little controlled earthquakes. In this video, you'll discover things you never suspected, and by the end, the main secret will be revealed that will forever change how you think about zinc. Zinc is the fourth most consumed metal in the world, right after iron, aluminum, and copper. That alone tells you just how critical it is for the global economy and industry. Annual worldwide zinc production runs somewhere between 12 and 13 million metric tons. We're talking massive volumes here, which really drives home how irreplaceable this metal is across hundreds of different applications. The main zinc mining regions are China, Australia, and Peru. These three countries together account for a huge chunk of global zinc ore production, making them the key players in the market. For instance, China isn't just the world's largest producer, it's also the biggest consumer of zinc, which reflects its massive industrial growth. Other major producers include India, the United States, Mexico, and Canada. As for reserves, the US Geological Survey estimates that global zinc reserves sit at around 250 million metric tons. Beyond that, there are what we call resource bases, essentially potential deposits that haven't been fully explored yet, or aren't economically viable to mine right now. These are estimated at over 1,800,000,000 tons. These numbers tell us that zinc, unlike some rare metals, will be around for many decades to come, even with consumption on the rise. The biggest user of zinc is the galvanizing industry, which uses it to protect steel from corrosion. This sector accounts for roughly 60% of all zinc produced. This shows just how critical zinc is for construction, automotive manufacturing, infrastructure production, and countless other industries where steel's strength and durability are essential. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a huge spike in resource demand. 15 to 20% of zinc is used to produce alloys like brass and die casting alloys. These alloys are used in making parts for cars, household appliances, toys, plumbing fixtures, and electronics. Another 10 to 15% goes into making zinc oxide and other chemical compounds. Zinc oxide has a ton of uses, from sunscreens and cosmetics to paints, ceramics, the rubber industry, and even animal feed supplements. Its antibacterial and protective properties make it a versatile ingredient. The rest of the zinc goes into battery production, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, since zinc is essential for the human immune system. When it comes to pricing, like most commodities, zinc prices fluctuate based on global supply and demand, economic cycles, and the situation in major producing and consuming countries. However, demand for zinc remains stable or growing, driven by urbanization, infrastructure development, and the worldwide need to protect metals from corrosion. This makes zinc an important indicator of global economic health. Most zinc is extracted from underground mines. These are entire underground cities stretching hundreds of feet and sometimes several miles beneath the Earth's surface. We're not talking about simple holes in the ground. These are networks of tunnels, shafts, ventilation systems, and hoisting structures. It all starts with exploration. Geologists work like detectives, searching for what's called ore bodies, sections of rock where the concentration of zinc is high enough to make mining it profitable. Now, zinc typically shows up as a sulfide ore, like sphalerite, and it almost always comes bundled with lead, silver, and sometimes copper. Once they've located a deposit, the real work begins: building the mine itself. This involves sinking vertical shafts that serve as the main access points for getting to the ore, hauling materials up and down, and moving equipment in and out. They also create horizontal tunnels, what miners call drifts, that lead straight to the ore veins. The actual ore extraction is where things get dynamic and risky. Miners bring in specialized gear, powerful drilling rigs that bore holes into the rock face, called blast holes. These holes get packed with explosives. Then comes the carefully controlled blast that breaks apart massive volumes of rock. Think of it like a controlled earthquake on a smaller scale. Dramatic, but completely under control. The dusty air is quickly removed by powerful ventilation systems, which also bring fresh air deep underground. The blasted ore is then loaded into massive underground haul trucks or onto conveyor belts using heavy-duty loaders. It's like a non-stop underground highway, constantly moving tons of ore to the main hoisting shafts. From there, the ore is lifted to the surface using powerful elevators or specialized conveyor systems that climb hundreds of feet vertically. At every stage, from drilling to hoisting, strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a processing plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore feed into crushers that break them down into smaller pieces with a deafening roar. This crushed ore then goes into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore gets ground down into an extremely fine powder, almost like flour. This is critical to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder gets mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then, air is pumped through this mixture, creating millions of tiny bubbles. Particles of zinc mineral latch onto these bubbles and float up to the surface, creating foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can pack up to 60% zinc. Since zinc often hangs out with lead, the plant might run several flotation cycles to separately pull out zinc concentrate from lead concentrate. The zinc concentrate you get, it's still not pure metal. It's got to go through metallurgical processing to turn into actual metallic zinc. And this is where we enter the world of extreme temperatures. If they're using the pyrometallurgical method, the zinc concentrate first gets roasted. The concentrate is heated in special furnaces at around 1,800 degrees Fahrenheit. This burns off the sulfur that's part of the sulfide ore, converting it into zinc oxide. During this process, the sulfur transforms into sulfur dioxide gas, which gets collected and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable byproduct. Next, the zinc oxide gets mixed with coal and heated to even higher temperatures, over 2,200 degrees Fahrenheit, sometimes reaching as high as 2,700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process takes place. The carbon strips away oxygen from the zinc oxide, releasing pure metallic zinc. And here's where that amazing evaporation effect happens. At these temperatures, the metallic zinc transitions into a gaseous state. Basically, it evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is way higher, zinc literally turns into vapor that rises up and gets captured in special condensers. There, the vapor cools down and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or pellets. Every year, over 500,000 bridges are built worldwide, but only a few of them challenge nature and time. To create a giant capable of withstanding thousands of tons of steel, windstorms, and earthquakes, engineers first dive into the very heart of the Earth, drilling the ground to a depth of over 100 meters, studying every layer of rock. Here, under water and mud, the foundation is born, on which the fate of the entire structure depends. How how do machines weighing as much as houses place piles with millimeter precision? And what will happen if even one of them shifts? Watch until the end, and you will learn what the engineering elite keeps silent about. The construction of long bridges begins long before the first steel beams or concrete supports appear. It all starts with a site investigation. Engineers analyze the soil, the strength of the current, the level of seismic activity, and the depth of the bottom, if it's a river or a bay. Often, special drilling rigs are used to take rock samples at depths of over 300 feet. These data determine the type of the future bridge: suspension, cable stayed, or beam. After this, a three-dimensional model is created. It takes everything into account: the load from transport, the force of the wind, temperature fluctuations, and even the possible impact of waves during storms. For bridges longer than half a mile, the permissible error in calculations can be no more than a few millimeters. Otherwise, the structure may lose stability. When the construction of a bridge moves from drawings to the actual ground, one of the most responsible and complex stages begins: the construction of the foundation, or the pile foundation. It is these structures, hidden under water or earth, that support the weight of the entire bridge: thousands of tons of steel, concrete, transport, and even wind load. Drilling cranes arrive at the site, giant machines with a long mast, a hydraulic drive, and interchangeable drills. They can reach the height of a 3-story building. Steel piles are brought to the worksite. Usually these are pipes with a diameter from 3 to 6 feet and a length of up to 100 feet. In marshy or marine areas, the piles are even larger, sometimes up to 150 feet. The drilling process takes place in stages. The machine is positioned with an accuracy of a few inches. For this, laser and GPS systems are used. Then the operator lowers the drill into the ground. The powerful rotation of the bit crushes the rock, and a hydraulic system pumps out the resulting pulp. In some areas where the soil is unstable, drilling is carried out with the immersion of casing pipes, metal casings that prevent the walls of the well from collapsing. When the hole reaches the specified depth, a steel pipe, the pile casing, is installed in it. A reinforcing cage is lowered inside, which strengthens the structure, after which concreting under pressure begins. Through a special hose, a concrete mixture is supplied from the bottom up, displacing water or mud. Thus, a dense, air-free mass is formed, which over time hardens into a monolith. In marine areas, floating barges with drilling rigs are used. Divers control the position of the pile underwater, and engineers monitor the process with ultrasonic sensors. In a strong current, drilling is carried out only during periods of calm, when the wave level is minimal. When the piles are installed, their tops are cut to the required height, and capitals are mounted on them. Large concrete blocks that unite several piles into one support. After this, pylons or columns are erected on these foundations, which are already visible above the surface. On land, temporary sites are simultaneously set up. These are logistics centers where beams, cables, reinforcement, and concrete sections are stored. Often, huge cranes 300 feet high are used here, which can lift blocks weighing over 200 tons. When the supports are ready, the turn of the superstructure comes. For bridges of great length, two main technologies are used: suspension and cable stayed. In a suspension bridge, the main load is carried by steel cables. To secure them, two massive towers, pylons, are first erected. Their height can reach 700 feet, as in the Golden Gate Bridge in San Francisco. The towers are assembled in sections, lifting each one with a crane and connecting them with bolts and welding. After the installation of the pylons, the main cables are stretched between them. This is a complex process that is carried out in stages. Thin steel wires, the thickness of a finger, are stretched one by the hundreds, until a main cable several feet thick is formed. Then vertical hangers are attached to these cables. They will hold the roadbed. In cable-stayed bridges, the main load is transmitted through inclined cables that go directly from the towers to the sections of the roadway. Such cables are made of steel strands with a polymer coating, capable of withstanding a load of over 500 tons. They are installed with the help of hydraulic winches, which precisely regulate the tension. The installation of the span sections is one of the most impressive stages in the construction of a bridge, when the giant engineering structure literally begins to connect the shores. Each section is a finished fragment of the road, made of high-strength concrete or steel at a specialized plant. There they are formed in giant molds, reinforced with steel bars, treated in thermal chambers for rapid strength gain, and then marked and checked for accuracy with a laser system. After this, these blocks are transported to the construction site. If the bridge is laid across a body of water, the sections are delivered by barges, floating platforms capable of withstanding hundreds of tons. On land, they are transported by multi-axle trailers with dozens of wheels, which evenly distribute the weight. The movement of such columns is usually accompanied by police, as each block can be from 100 to 400 tons and over 100 feet long. At the construction site, floating cranes or lifters are already waiting. These are powerful lifting systems capable of lifting a load of over 500 tons. Most often, such cranes are mounted on pontoons or mobile platforms that can accurately maneuver over the water. During the lift, the crane operator coordinates his actions with the engineers who are on the bridge supports. Every movement is a matter of inch precision, as the section needs not just to be lifted, but placed perfectly in the design position. When the block is suspended above the supports, it is slowly lowered. Workers fix the position with the help of special guide pins and laser marks. Then dampers and high-strength connecting bolts are installed in the joints of the sections. It is important that the sections fit together without the slightest misalignment. Even an error of half an inch can cause uneven load. Next, the joints are filled with cement mortar under pressure, which fills all the voids and forms a monolithic connection. In some types of bridges, post-tensioning cables are used, steel strands that are threaded through the internal channels of the sections and tensioned with hydraulic jacks, providing additional strength. If the bridge is being built over the sea, the installation is even more complicated. Barges with sections are tied to positions with an accuracy of a few feet using GPS, and the lifting takes place only in calm seas. Often at night, when the wind is weaker and the waves are minimal, the crane slowly lifts a section. The process can take several hours. From the side, it looks like a giant aerial operation. A steel or concrete slab, as huge as a two-story building, smoothly rises above the water or a gorge, moving with an accuracy of a few centimeters. When it is fixed between the supports, the bridge literally grows. Another span, another few tens of feet of road, which bring it closer to completion. In parallel with the installation of the roadbed, communications are laid, lighting systems, communication wires, pipes for rainwater drainage. Most bridges have sensors that measure vibrations, temperature, the tension of the cables, and even the concentration of salts in the air. These data are constantly transmitted to a control center. When the main structure is completed, the road surface work begins. The surface consists of several layers. The first layer is a special anti-corrosion compound that protects the concrete and metal. Next, waterproofing is applied, then several layers of asphalt or polymer concrete, about 4 inches thick. For suspension bridges, lighter materials are used to reduce the load. The final stage is the installation of railings, noise barriers, and the painting of steel elements. The painting has not only an aesthetic function, it also protects the metal from corrosion. For bridges over the sea, paints with the addition of zinc are used, which create a stable protective layer. After the completion of all work, the bridge undergoes a series of tests. Special trucks are loaded onto it to check how the structure reacts to weight. Vibration tests are also conducted. Engineers check how the bridge behaves during wind or the movement of trains and cars. If the indicators meet the standards, the object is put into operation. Imagine, glass that once shattered into deadly sharp fragments now saves lives. How did humanity transform a fragile substance into armor for a car? And what is hidden behind this seemingly simple transparency? Every year, over 100 million square meters of automotive glass are produced worldwide, enough to cover the area of an entire country. But the real magic happens where molten stone is transformed into a perfectly smooth surface, in furnaces that reach temperatures of over 2,700 degrees Fahrenheit. How did ordinary quartz sand become the foundation of safety technology, without which we cannot imagine modern transport? Watch until the end, and you will learn what accidental experiment changed the history of automobiles forever. The history of automotive glass production is closely linked to the development of the automotive industry, which emerged at the end of the 19th century. The glass used in cars today has come a long way in improvements, making it safer, stronger, and more functional. When the first cars began to appear, they were initially not equipped with glass at all. The open body design only partially protected passengers, and dust, wind, insects, and other hazards made trips very uncomfortable. Later, as cars became faster, the need to install protection for the driver and passengers arose. The windshield began to be made from ordinary window glass, which, although it provided some protection, had a serious drawback. During accidents, it shattered into large, sharp fragments, leading to numerous injuries. The first revolutionary discovery in the field of automotive glass was the creation of laminated glass. This happened by chance. In 1903, the French chemist Edouard Benedictus accidentally dropped a flask with a nitrocellulose coating. The glass cracked but remained whole thanks to a thin layer of plastic. This accident inspired the scientist to create multi-layered glass, which later became the basis for Triplex. Already in the 1910s, laminated glass began to be used in premium class cars. Its construction consisted of 2 layers of glass, between which a thin, transparent film was placed. In the event of an impact, the glass did not shatter, and the cracks remained on the film. In the 1920s, laminated glass began to be actively used in the production of windshields. Its main advantage was increased safety. Even during serious accidents, the fragments did not fly apart, but remained in the polymer layer. The next stage in the development of automotive glass came in the 1930s, when the technology for producing tempered glass was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it broke, it disintegrated into small pieces with blunt edges, which minimized injuries. In the mid-20th century, tempered glass began to be used for the side and rear windows of cars. It was cheaper to produce compared to Triplex and provided a sufficient level of safety for these parts of the car. In the 1950s and 60s, automotive glass became even more perfect thanks to the development of technology. During this time, various important changes took place. Improvement of Triplex. The development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production. The automation of production processes allowed for a reduction in the cost of automotive glass, which made it more accessible to the mass market. Sun protection coatings. For the first time, special coatings began to be used that blocked ultraviolet light and reduced the heating of the car's interior. One of the most important technological breakthroughs in glass production was the invention of the float method in 1959. This technology, developed by the British company Pilkington, allowed for the production of perfectly smooth glass by spreading the liquid glass mass over the surface of molten tin. Thanks to this method, glass became more uniform, strong, and accessible for mass production. The float method is still the basis of automotive glass production today, ensuring its precise dimensions, surface smoothness, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 1960s, heating filaments began to be installed in the rear windows of cars, which prevented fogging and freezing of the glass. In the 1980s, glass with special metal coatings appeared, which reflected sunlight and reduced the heating of the interior. Glass with ultraviolet protection. Thanks to the introduction of new technologies, automotive glass began to provide almost complete protection against harmful radiation. And then we begin the modern period of automotive glass production, which we will talk about now. And we will start with glass for cars. Automotive glass is divided into several types depending on its purpose and production technology. Windshield. Usually this is multi-layered glass, which consists of 2 layers of glass, between which a polymer film is located. Such a design ensures that upon damage, the glass does not fly into sharp fragments. Side and rear glass. Most often this is tempered glass, which upon impact breaks into small blunt-angled pieces, which reduces the risk of injury. Panoramic roofs or other special types of glass. Laminated or tempered glass with a special coating for protection against ultraviolet radiation is often used. The main components of glass are natural materials that are mixed in certain proportions to obtain the desired properties. Quartz sand is the main component of glass, which ensures its transparency. It must be extremely clean and contain a minimum of impurities. Soda is added to lower the melting temperature of the glass. Lime improves the mechanical stability and chemical properties of the glass. Additional additives used to correct color, transparency, resistance to ultraviolet light, and other properties. The raw material is cleaned, dried, and crushed to a uniform state. It is important that impurities that can affect the quality of the glass are maximally eliminated. After preparing the raw material, it is loaded into special furnaces for melting. This stage includes several important moments. Let's look at them together. Melting temperature. A temperature of about 2,732 degrees Fahrenheit is used to form the glass mass. In the melting process, the raw material turns into a uniform viscous liquid. Homogenization. The glass mass is mixed for an even distribution of components. This is important to avoid air bubbles or inhomogeneities in the finished product. Furnaces for melting glass are equipped with modern temperature control systems and process automation, which ensures high quality of the final product. After melting, the glass mass undergoes a forming process, which in modern production is most often performed using the float method technology. Feeding the glass mass. The liquid glass flows out of the furnace and onto a bath of molten tin. Thanks to the high density of tin, the glass mass spreads evenly over its surface. Under the influence of its own weight, the glass forms a perfectly even and smooth surface. By gradually lowering the temperature, the glass acquires hardness. At the exit of the bath, it can already be processed. The float method allows for the production of glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions required for automotive production. Automated cutting machines ensure the accuracy of the work. To prevent the formation of cracks and chips, the edges of the glass are ground. Each sheet is checked for defects, such as microcracks, bubbles, or other damage. Next, to ensure the strength and safety of automotive glass, it is subjected to a tempering process. The glass is heated to a temperature of about 1,112 degrees Fahrenheit. Then, the surface of the glass is rapidly cooled by streams of air, while the inner layers cool more slowly. As a result, stress is created, which increases impact resistance. Tempered glass, when destroyed, breaks into small, safe fragments, which minimizes the risk of injury. Next, for the windshield, Triplex is used, a construction of glass and polymer film. Its production includes several stages. Joining the layers. A polymer film is placed between 2 glass sheets. The construction is placed in a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to a temperature of 284 Fahrenheit under high pressure. This ensures a strong connection of the layers. Triplex has high impact resistance, and upon damage, it remains in the polymer film, which ensures the safety of the driver and passengers. Next, to improve the properties of automotive glass, various coatings are applied to it. Anti-reflective coatings reduce glare from the sun or headlights of other cars. Ultraviolet protection. Special layers block harmful ultraviolet radiation. Hydrophobic coatings ensure that water runs off the surface of the glass. Heating elements. Thin heating filaments can be embedded in the windshield, which facilitate the removal of ice or fogging. To achieve the desired shape, special thermoforming installations are used. The glass is heated to a temperature at which it becomes plastic and is formed according to the given parameters. And so, We have reached the final stage. During it, each product undergoes a thorough check. Transparency and the presence of defects are checked. Next, the glass is tested for impact resistance and endurance to loads. Compliance with standards. The accuracy of dimensions, shape, and other parameters are checked. Then the finished automotive glass is packaged in such a way as to avoid damage during transportation. It is delivered to car factories or service centers, where it is installed in vehicles. The production of automotive glass is a high-tech process that combines physics, chemistry, and engineering. Thanks to modern technologies and strict quality control standards, automotive glass ensures safety, comfort, and durability. And just imagine how many stages the automotive glass had to go through for us to be able to monitor safety on the road and have the opportunity to admire the wonderful landscapes. It seems incredible to me. And you? Every year, over 900,000 aircraft engines are manufactured worldwide, hearts that push giants of the sky on journeys across continents. But have you ever wondered how this metal monster is born? One that operates in conditions of over 2,000 degrees and at speeds that could destroy any metal. Inside it, titanium bones, a nickel heart, and composite lungs. And then, technologies resembling alchemy, single crystals, vacuum casting, and 3D metal printing. But the main secret is not in how it's created, but what's hidden inside. Watch until the end, and you'll learn something that even Boeing engineers keep quiet about. The turbofan engines that push giants of the sky, like Boeing and Airbus planes, resemble something out of science fiction. However, they are a true embodiment of engineering genius. How are these amazing machines assembled from tens of thousands of parts and ingredients, like a puzzle? Ordinary metals are not suitable for their manufacture. After all, the engine must operate in conditions where the temperature can exceed 1,800 degrees Fahrenheit. This is a real inferno, and ordinary steel simply wouldn't withstand it. This is where titanium alloys come on stage. Lightweight, strong, and able to not melt in extreme heat. And for the hottest zones of the engine, nickel-based superalloys are used. By the way, this isn't just metal, it's 21st century alchemy. Composites, particularly carbon fibers, are used for the fan to reduce weight while maintaining strength. Such a high temperature arises from the process of burning fuel in the combustion chamber, one of the most important elements of a turbofan engine. During engine operation, aviation fuel, usually jet fuel, is mixed with air and ignites, forming hot gases. These gases are literally accelerated to insane speeds and temperatures, over 1,800 degrees Fahrenheit, and sometimes even up to 2,700 in modern engines. This level of heat is needed to get the most efficient thrust. That is, the hotter and faster the gases, the stronger the energy flow that spins the turbine and provides the aircraft's motion. And here lies the main challenge. The engine must not only withstand these extreme conditions, but also operate stably, without the slightest failure. That's why it uses super technological materials, like titanium alloys and special composites, which can withstand both high temperature and insane mechanical stress. You know what's incredible about the process of creating an engine? That even individual parts, like the turbine blades, are created with micron precision. For example, the blades are cast in a vacuum so that there isn't even the smallest crack inside. Some of them are formed to have a single crystal structure. That's when a piece of metal has no seams at all. But that's not all. 3D printing? Yes, that's used too. For example, for complex parts that are impossible to make with traditional casting. The turbine blades are the heart of the engine. They operate in the hottest zone and convert the energy of the hot gases into rotational motion. First, a model of the blade is created from wax. Yes, it looks almost like artistic sculpting, only here, precision down to the micron is important. This wax sample is then dipped into a special ceramic solution, which gradually dries, forming a strong mold. This mold is like a perfect cast of the future blade. The wax inside is melted and removed, and the ceramic is ready for the most important stage. Next, the show begins. In a special furnace, superalloys are melted, which include nickel, chromium, and other metals capable of withstanding temperatures above 2,000 degrees Fahrenheit. This molten metal is poured into the ceramic mold. But the secret is not only in the material, but also in the way it's done. To make the blade withstand gigantic temperatures and loads, it is often cast as a single crystal. This means that the entire piece of metal has no seams, micro cracks, or different grains, as in ordinary metal. Why is this important? Seams or micro cracks in such conditions are like a minefield. One mistake, and the blade shatters. Single crystals are grown through very slow cooling. The mold with the molten metal is gradually lowered into the cooling zone of the furnace. This process can take several days, but the result is a perfectly strong and durable blade. When the metal cools, the ceramic mold is broken, and the blade undergoes thorough grinding. A special heat-resistant coating may be applied to the surface so that it can withstand extreme temperatures even longer. And so, each blade is checked separately. If there is even the slightest defect, it doesn't go any further. Fuel injection nozzles, combustion chamber parts, or even compressor blades in aviation are made using 3D printing. For example, the company GE Aviation prints nozzles for its engines that weigh 25% less, but are 5 times stronger than traditional ones. Layer by layer, from powder and light, parts are created that allow planes to fly faster, farther, and more economically. First, engineers create a digital 3D model of the part with maximum precision. Here, every curved surface or cavity matters. Why? Because these parts often work in places where a millimeter can change everything, from the engine's efficiency to its reliability. The digital model becomes a map for the 3D printer, which knows where and how to create the required shape. Instead of the usual piece of metal, an ultrafine powder is used here. For example, of titanium, nickel, or Inconel, this is a super aluminum alloy. It looks like sand, but with particles so fine that they are almost invisible to the naked eye. The powder is poured into a special reservoir, and it becomes the building material. The principle of the printer's operation is simple but ingenious. It melts the powder using a laser or an electron beam. The laser heats the powder to such a temperature that it literally fuses into a homogeneous metal structure. Then the next layer of powder is applied, and the process is repeated. This method is called selective laser sintering or melting. And what's cool is that 3D printing allows for the creation of even the most complex geometric shapes. For example, parts with internal cooling channels, which are generally impossible to produce by casting or milling. You know, in traditional manufacturing, you often have to first make a large part and then cut off all the excess. This is not only time-consuming, but also expensive because a lot of material is wasted. But 3D printing works differently. Only what is needed is created without waste. The resulting part is not yet completely ready. After printing, it undergoes heat treatment. It is heated and gradually cooled to relieve internal stresses in the metal. Then comes the final grinding, polishing, or mechanical processing if precision needs to be adjusted. And of course, each part undergoes thorough testing. After all, everything here is serious. If a part does not withstand the load, the consequences can be catastrophic. The engine assembly takes place in a huge hangar, where every foot of space is occupied by tools, engine parts, and people in overalls who are intently working on something extraordinary. This place is the final stage of creating an aircraft engine. Here, individual parts, such as blades, compressors, combustion chambers, and casings, are transformed into a single whole. ready to lift an airplane into the sky. It all starts with the engine casing, which resembles a giant metal cylinder. This is the skeleton to which all other parts will be attached. The casing is made of titanium or nickel alloys, as it will have to withstand insane loads. Engineers work like watchmakers. The casing is secured in a huge machine tool to ensure everything is perfectly level. Next come the compressors, several rows of blades that are responsible for compressing the air before it is fed into the combustion chamber. The blades are installed one by one, as if decorating a giant wheel. Each one is checked by hand, as the slightest defect can ruin the entire job. After the compressors, it's the turbine's turn. These are the blades that convert the energy of hot gases into motion. The turbines are placed so precisely that the distance between the blades and the casing walls is sometimes measured in microns. Next, the combustion chamber is installed, the real hell of the engine. Here, compressed air is mixed with fuel and burned. Engineers install special nozzles that ensure a uniform fuel supply. And here, everything must be perfect. An incorrect nozzle angle, and the engine can lose efficiency or even fail. A central shaft runs through the entire engine, a kind of backbone. At one end of the shaft, a fan in the form of a huge wheel is attached to the front of the engine. At the other end, the turbine. When the turbine rotates under the influence of hot gases, the shaft transmits this energy to the fan, which sucks in air. Special robots are used to install the shaft. This part of the process requires surgical precision, as even a microscopic misalignment can cause vibrations that will kill the engine. When the internal part of the engine is assembled, the external systems are added. Fuel pipes that supply fuel to the combustion chamber, an oil system that provides lubrication for all moving parts, and electronics because the engine is literally packed with sensors that monitor temperature, pressure, speed, and much more. These elements are attached using cables, tubes, and bolts that must withstand not only vibration but also extreme temperatures. After the assembly is complete, the engine is not sent to the aircraft right away. First, it is attached to a test stand, where real flight conditions are simulated. From takeoff to turbulence at an altitude of almost 33,000 feet. This is the most spectacular stage. Starting the engine at full power is accompanied by a roar that can be heard for several miles and bright gas streams. The engine runs under load for hours, and engineers check it for strength, endurance, and efficiency. When the engine passes all tests, it is disassembled, the main components are checked again, and then it is finally assembled. The finished engine is packaged and transported to a Boeing or Airbus factory, where it becomes part of a new aircraft. And so, part by part, engineers create the heart of an airplane, which is capable of carrying thousands of passengers across continents. Isn't that a modern masterpiece? Let me know if you would like to see more videos like this. Every year, over 50 million tons of batteries are discarded worldwide, from small AA batteries to giant electric vehicle batteries. Imagine a mountain of metal reaching the size of Mount Everest, filled with toxic substances. But now, part of this mountain gets a second life. Behind the thick walls of factories, old batteries are put into shredders where steel blades tear them apart. They are frozen with liquid nitrogen and turned into a black powder that will once again become lithium or cobalt. Watch until the end. You will see how a new future for energy is born from waste. Battery collection starts with people. Private individuals turn in batteries from phones and laptops. Car service centers, batteries from electric vehicles, and also businesses that use a lot of equipment. Collection points are in electronics stores, supermarkets, or specialized collection centers. Here, everything is as manual as possible. People bring batteries, and staff or volunteers accept and record them. Old batteries from factories or car service centers are delivered by trucks to large collection centers. Special battery containers have sensors that determine the fill level. When a container is almost full, a signal is sent to the collection company. Some companies use drones to check the fill level of large containers in remote locations. Batteries are sorted by type by people and machines, because batteries come in different types: lithium-ion, nickel metal hydride, lead acid, and so on. They cannot be mixed during recycling. At small collection points, for example, in cities, batteries are sorted manually by workers. They rely on markings, labels, and appearance such as shape and case color. Small batteries from smartphones or laptops go in one direction, and large batteries from electric vehicles in another. At large enterprises, automatic sorting lines are in operation. Machines scan batteries by size, weight, and the type of metals they contain. X-ray analysis or spectroscopy is used to determine exactly which battery is in front of the machine. After scanning, the batteries move along a conveyor to different bins, where they await the next stage. Even at automated factories, people are present. Operators check whether the machines are sorting the batteries correctly. If a problem arises, for example, a torn battery case or a missing label, people intervene and sort manually. Batteries from electric vehicles or solar stations are too large for automatic lines. This is where robots come into play, helping to disassemble these giant blocks into smaller sections. Then they are sorted by material. No matter how much machines do, people are still the most important in the sorting process. These are mainly the workers at collection points and the operators of sorting lines. Specialists assess damaged batteries manually because machines cannot yet recognize all defects. Machines work faster, but for now, they can't do without people. Ultimately, every correctly sorted battery is a chance to recover rare earth metals and reduce environmental harm. Next, the batteries need to be shredded. They enter real metal jaws. The batteries are loaded into a machine that looks like a huge shredder, equipped with steel blades. The blades are so powerful that they can even shred the body of an electric car. Metal chaos ensues. The sound of tearing, grinding, and cracking. The batteries are literally ripped to shreds. Since the batteries can be charged, they first undergo freezing in liquid nitrogen. This cools the metals and reduces the risk of ignition. Some shredders operate in sealed chambers with inert gases to exclude contact with oxygen. There is also a more spectacular option. In some places, a controlled current is first used for ignition. The battery literally burns out, leaving only the metals. The batteries are shredded into pieces from a few centimeters to a crumb, depending on the type of shredder. The blades rotate at a speed of over 2,000 revolutions per minute, and metal fragments fly in all directions with a clang inside a protected chamber. The shredded pieces pass through magnetic separators, which with filigree precision extract ferromagnetic metals, for example, nickel or cobalt. Fragments of other materials continue their journey along the conveyor. A fine black powder, known as black mass, settles in special containers. This is where the treasures are hidden: lithium, cobalt, manganese. Machines literally suck up the powder with dust collectors to gather even the microparticles. Residues that are not suitable for recycling, meaning plastic and traces of electrolytes, are washed away with special streams of liquid. At this stage, hydraulic crushers are used, which turn the remnants into a slurry that is easy to filter. Engineers monitor the condition of the shredders and the temperature level inside the chambers. Specialists work with the results of the shredding. They check whether all the metals have been separated and whether any extra impurities remain. If a battery is charged and has defects, it can literally explode during shredding. But the system controls this. The explosion is extinguished by gases, and the process does not stop. After the batteries are shredded and that precious black powder is obtained, science in action, as they say, begins. The metals that seem to be hidden forever are extracted using two main methods: hydrometallurgy and pyrometallurgy. And although this may sound a bit technical, the processes themselves are extremely interesting. So what does it look like? Battery fragments are immersed in special acid solutions. There are huge tanks where a yellowish-green liquid is bubbling. This could be sulfuric or hydrochloric acid. During immersion, a reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve in this soup. To extract the desired metal, a clever trick is used: ion extraction. Special reagents, for example, organic compounds, are added to the liquid which capture a specific metal, like a magnet. As a result, each metal settles into a separate layer. When the metals are separated, they are precipitated in the form of salts or hydroxides. They look like small white or colored crystals. For example, lithium precipitates as lithium carbonate, a powder that looks like fine sugar. Cobalt becomes a bright blue precipitate, and nickel, a pale green one. If hydrometallurgy is a gentle approach, then pyrometallurgy is more like shock therapy for metals. Here, everything literally burns and melts. The black mass is loaded into a huge arc furnace, where the temperature reaches almost 3,000 degrees Fahrenheit. The metals melt into a liquid mass, and the plastic and other residues simply burn up. The metals stratify, like oil and water, but at the temperature of molten lava. Several layers form in the furnace. Heavy metals, meaning cobalt and nickel, settle to the bottom, while lithium remains in the slag. This is the upper, lighter layer. Then this slag is broken up and processed separately to extract the lithium. After cooling, the metals take the form of small ingots, shiny, smooth, and ready for reuse. The cooling after the pyrometallurgical process usually happens in a controlled manner. After all, if you just let the molten metals cool on their own, it could take hours and sometimes even days. In addition, such cooling can create an uneven metal structure. This will affect the quality of the final product. Therefore, they are usually cooled in special chambers, where the cooling rate can be regulated. If the controlled cooling is air-based, the ingots are left on a conveyor under powerful fans. It's like a giant hairdryer that quickly cools the metal surface. If it's water cooling, for a faster process, the metal ingots can be immersed in a bath of water or special liquids. This is a huge tank where the red-hot ingot, upon entering the water, releases clouds of steam. It looks quite spectacular. Sometimes there is combined cooling. This is when some stages begin with air cooling and then are completed with water cooling to reduce stress in the metal. Controlled cooling ensures a uniform structure of the metals, which is critically important for their reuse in batteries. This reduces cracks or defects that can arise from sharp temperature changes. The obtained lithium is used to create new batteries, those that will charge electric cars or even your phones. Nickel can become part of turbines that generate energy from wind, and cobalt, an important component of medical equipment. So we are literally closing the loop. Old batteries give life to new technologies. Discarded batteries can turn into a real environmental disaster. First, they contain toxic substances that pollute the soil and water. Second, the mining of new rare earth metals not only depletes natural resources, but also harms the environment. Recycling solves both of these problems. You know what else is cool? The more batteries we recycle, the less we depend on mining new materials. This is a direct path to sustainable development. Despite the popularity of lithium, only 1% of this metal is currently recycled. The main reason is the high cost and complexity of the process. But researchers are developing new technologies that could change the situation in the coming years. Interestingly, even now, electric car manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plant to maintain control over valuable materials. Every year, humanity creates energy that on one hand saves cities, and on the other, hides an incredible story of transformations. One average reactor produces 1,000 megawatts and requires only 27 tons of enriched uranium per year, the weight of 3 school buses. But to get these 27 tons, you have to mine and process over 100,000 tons of ore. In this video, we will follow the path from a noisy mine and acid vats to supersonic centrifuges, furnaces, and tiny fuel pellets. Every step is chemistry, giant machines, and unexpected risks that you are almost never told about. Stay until the end, and I will reveal one secret to you that will change your perception of atomic energy. An average American nuclear reactor has a capacity of about 1,000 megawatts. For it to operate for 1 year, it needs approximately 27 tons of enriched uranium fuel. 27 tons is the weight of about 3 school buses. And now let's compare. To produce the same amount of electricity, a coal-fired power plant needs to burn over 3 million tons of coal. That's over 10 million barrels of oil. Nuclear fuel is the highest form of energy concentration that humanity has ever created. But to get these 27 tons of fuel, you need to start with a much, much larger amount of raw material. The chain of transformations is simply staggering. To produce those same 27 tons of enriched uranium fuel, you need to start with 215 tons of uranium concentrate. And to get those 215 tons of concentrate, you need to mine and process over 100,000 tons of uranium ore. Imagine a giant mountain of stone, the size of a multi-story building, which ultimately turns into a volume of fuel that fits in one truck. This shows how dispersed uranium is in nature and how complex the process of its concentration is. It all begins in the roaring chaos of a uranium mine. Imagine a deep shaft or a giant open-pit quarry where huge machines with a deafening roar bite into the rock. The air here is thick with dust, and every stone that is brought to the surface looks absolutely ordinary, just a gray, dull granite or sandstone. The uranium here is invisible. It is dispersed in the rock in the form of tiny microscopic inclusions, and its concentration is incredibly low, often less than 1%. This means that to get 1 pound of uranium, you need to mine and process hundreds or even thousands of pounds of barren rock. Dump trucks, loaded to the brim, take this ore to a nearby processing plant that hums. The first stop is the primary crusher. This is a giant steel maw that, with a deafening crunch, crushes large stone blocks into pieces the size of a fist. Then, this crushed stone goes by conveyor to a huge mill. A giant rotating drum, filled with steel balls, resembles an industrial washing machine for stones. Here, in a continuous roar, the ore is ground into the finest, grey sand, almost dust. And now the real chemistry begins, a process called leaching. This grey sand is mixed with water, forming a thick pulp, and pumped into huge vats, the size of a small house. A powerful chemical solvent is added to these vats, most often sulfuric acid. This acid, like a hungry predator, begins to eat the uranium, pulling it out of the solid rock and turning it into a liquid, dissolved state. This process lasts for many hours, while the entire mixture is continuously stirred. As a result, we get 2 things. On one hand, tons of wet, now unnecessary sand, so-called tailings, which are toxic waste, and on the other, a murky, greenish-yellow liquid containing our precious uranium. This liquid needs to be cleaned and concentrated. It is passed through a series of columns filled with special ion exchange resins. Imagine this as a high-tech water filter. The resins, like a magnet, pull out only the uranium ions from the solution, letting everything else pass by. Then these resins are washed with another solution, which washes the concentrated uranium off them. And so, finally, our final product is precipitated from this clean, saturated liquid. By adding ammonia or hydrogen peroxide, the uranium is forced to fall out of the solution in the form of a bright yellow, thick precipitate. This precipitate is filtered, dried in furnaces, and at the output, we get the same famous yellow cake, a heavy, radioactive, mustard-like powder. This is the uranium oxide concentrate, the first step on the long path to clean energy. The next step is purification to an absolute, almost unearthly purity. The yellow cake is sent to a special plant, where it is dissolved and, with the help of complex chemical processes, such as solvent extraction, all impurities are removed from it. The goal is to obtain perfectly pure uranium dioxide. But here the main problem arises, which is at the heart of all nuclear energy. In this perfectly pure uranium, 99.3% is the stable, lazy isotope uranium-238, which cannot sustain a chain reaction. And only 0.7% is the energetic, unstable isotope uranium-235, which is our fuel. They are chemical twins, and it is impossible to separate them by chemistry. To make the reactor work, we need to increase the concentration of this energetic uranium-235 from 0.7% to 3 or 5%. To begin enrichment, the solid uranium must be converted into a gas. It is treated with hydrofluoric acid, turning it into uranium tetrafluoride, and then with fluorine to obtain uranium hexafluoride. This is a very corrosive and dangerous compound, which has a unique property. It becomes a gas at a temperature slightly above room temperature, and so this gas, packed in special containers, is sent to an enrichment plant. Imagine a giant, noisy workshop the size of several football fields, filled with thousands of identical, tall, metal column-like devices. These are gas centrifuges. Each of them is a high-tech top that rotates at supersonic speed, making tens of thousands of revolutions per minute. When our uranium gas is pumped inside, the magic of physics begins. The heavier gas molecules with uranium-238, under the action of centrifugal force, are pressed against the walls of the centrifuge, and the very slightly lighter molecules with uranium-235 remain closer to the center. This is a microscopic difference, but it is enough. Special tubes take the gas from the center, which now contains a little more uranium-235, and send it to the next centrifuge in the cascade. And the depleted gas from the walls is diverted to the side. To achieve the required concentration of 3 or 5%, the gas must pass through thousands of such centrifuges. This is an incredibly long and energy-intensive process. When we have finally obtained our uranium hexafluoride, enriched to the required level, it needs to be converted back into a solid material suitable for fuel. With the help of chemical reactions, it is turned into a black powder of uranium dioxide. But this is not just any powder. Each of its particles has a perfectly calibrated size and shape. Now the most interesting part begins, the creation of fuel pellets. This black, heavy powder is sent to a press. Imagine a high-precision pharmaceutical press, only instead of medicine, it stamps radioactive pellets. It compresses the powder with incredible force, turning it into small, dense, perfectly cylindrical granules, or pellets. They are still brittle, like chalk. To give them strength, they are sent to a furnace. But this is not an ordinary furnace. This is a high-temperature furnace, filled with hydrogen to prevent oxidation. There, at a temperature of over 3,000 degrees Fahrenheit, these pellets are baked for many hours. During this process, called sintering, the powder particles fuse together, and the pellet turns into an extremely hard, dense, ceramic-like substance. It becomes so strong that it can withstand the extreme temperatures and pressures inside a nuclear reactor. Each pellet after this undergoes laser control, which checks its dimensions with micron accuracy. The next step is assembly. These small black ceramic candies are carefully, one by one, loaded into long, thin tubes. These tubes, about 13 feet long, are not made of steel, but of a special zirconium alloy called zircaloy. This material is unique in that it is very strong, resistant to corrosion, and most importantly, almost transparent to neutrons, allowing the chain reaction to proceed without hindrance. When the tube is completely filled with pellets, it is filled with an inert gas, usually helium, to improve heat transfer, and hermetically sealed at both ends. Now, it is not just a tube with pellets, it is a fuel element. And the final stage is the creation of a fuel assembly. Several hundred such ready-made fuel elements, for example 17 by 17, which gives a total of 289 pieces, are assembled into one large square bundle. They are held together by special spacer grids. This ready-made assembly, which looks like a giant, high-tech quiver with arrows, is the final product. It weighs about half a ton and is ready for shipment to a nuclear power plant. And so, having passed an incredibly long and complex path from an ordinary stone through chemical transformations, supersonic rotation in centrifuges, infernal baking, and precise, almost clockwork assembly, this concentrated bundle of energy is born, ready to quietly and reliably produce millions of kilowatts of clean electricity for several years.